So I wanted to do a couple of examples of where you're trying to determine the pH of a solution where it contains a weak base. All right. Unfortunately, I don't have guided notes for this, so you're just going to have to do these by hand. So in this problem, calculate the pH of a solution if you dissolved 3.5 moles of methylamine, which has this formula right here, in 1.75 liters of total aqueous solution. All right. So the first thing that we're going to do is we need to calculate what the molarity of this stuff in solution would be. And again, molarity is moles per liter of solution. So we can go and calculate that. Here's your moles of the methylamine. Here's the total amount of solution. We can calculate that that would be 2.00 molar. All right, notice the way I report this, it's got 3 sig figs because you've got 3 sig figs in both of these numbers right here. All right, so some additional information that we're going to need to do this problem has to do with the strength of this particular base. All right, and the strength of bases is given by the pKb or the Kb. All right, so for that, we're going to go to the data table, and this is actually in table 21. And you click through, and we can find methylamine right here. All right, methylamine, you can see that it's reported pKb is 3.34, and we are going to use that. So 3.34, and we can do 10 raised to the negative 3.34 to get to our Kb. All right, so this information is going to come in handy later. All right, so the next thing, all right, we want to draw the generic base reaction. All right, so remember when we were doing this problem for weak acids, we showed the generic Bronsted-Lowry equation that you would have for acids, where we show an acid donating a hydrogen to water and making H3O+. Well, the standard Bronsted-Lowry definition equation for a base shows the base accepting a hydrogen or an H+ from water to give your conjugate acid plus the hydroxide ion. All right, and so again, I'm just wanting to show this. This right here, the base in this situation, could either be represented as A-, and if you're showing this as A-, the corresponding conjugate acid would be HA. But alternatively, sometimes you'll see it referred to as B, capital B, and if you refer to the base as capital B, then the corresponding conjugate acid would be BH+. All right, either way, remember it's all relative. In both cases, these guys over here have one more hydrogen and one higher charge than the corresponding thing over here. All right, so what are we going to do with this? We're going to set up the same type of chart that we did before. All right, where we have a starting condition, we assume a certain amount of change is going to occur from that starting position, and then that's going to allow us to have an expression for what the equilibrium or what the final concentration of these things would be in the solution. All right, so we're starting off with 2 molar of your methylamine. That's what we calculated here. At the very start of this, we would assume that we have 0 of these guys right here. And since it's a 1 to 1 to 1 to 1 ratio, for every time this guy goes down by some amount, these guys right here go up by the same amount. All right, and so we can calculate these expressions right here, which show those concentrations. All right, so we could write a Kb expression. So remember, this is the equation that we use to define the Kb, and so in the Kb expression, we take our conjugate acid right here, and we put that up top. We put the hydroxide up top as well, and we put the base down here in the denominator. All right. So again, these are what those would correspond to generically. And if we look at what we came up from this chart, let's substitute what we had for these guys. So for this guy right here, you can see that it's X. For this guy right here, you can see that it's X. That's why we plug those in, and this guy right here goes in the denominator. And we know from our little earlier work that the Kb was this value. So all of that is going to equal this value. All right, so what we are going to do, and by the way, I know that I mentioned earlier that we're the number had to be smaller than 10 to the minus fourth. This number right here is slightly larger than 10 to the minus fourth, but we're still going to do that assumption where we assume that this right here is, we can get rid of the minus x. All right, and that's what we did right here. X squared over 2 is equal to this value right here. We end up solving for x. And one thing that we notice is that x happens to be the final concentration of hydroxide. All right, and so therefore we can say that this right here, and I could put a molar after that. That's going to be the final concentration of hydroxide. And what we know from that is we can do the POH. All right, that's going to be the negative log of whatever that is. So the POH we can calculate to be 1.52. And from that we can calculate the pH, which is going to be just 14 minus that number, 12.48. All right. Okay, so in this next problem, I'll go ahead and admit that this is a little bit more complicated, but it uses a lot of the same principles that we showed in the previous example. All right, and so the question is, what is the pH of a 2.5 molar solution of sodium phenolate? All right, and I've gone ahead and shown the structure, both the structure here and the formula for sodium phenolate. All right, so essentially what sodium phenolate is it's the sodium, what's called the sodium salt of phenol. All right, so it's an ionic compound, and for example, if we can make the comparison to sodium chloride. Sodium chloride is a positively charged sodium ion with a negatively charged chloride ion. All right, this right here, this part right here, is essentially a big polyatomic ion where there's a formal negative charge on this oxygen. So the entire charge on this entire part right here would be -1. So it's just an ionic compound where this is your +1 ion and this is your -1 ion. All right, and we'll talk a little bit more about that in a second. So when sodium phenolate dissolves, it's going to break apart into its ions just in the same way something like sodium chloride would. All right, so when this dissolves, it's going to break apart into its positive ion, which is sodium, and its negative ion, which is, this is what you would call a phenolate ion or a phenolate anion because it's a negative ion. And what we can do is, since we had a 2.5 molar solution, if 2.5 molar of this were to dissolve, well, for every one of this, you generate one of this and one of this. So we know that the concentration of this phenolate that's dissolved in the solution would be 2.5 molar. All right, at least at the beginning, at least before, as you'll see in a second, it acts as a base. All right, so but like this would be the starting position for that. All right, so I want to give a little perspective on what this thing is. All right, because if this is essentially what we're doing is we're saying that this thing right here is a base, and we're going to be calculating a pH base of the solution based on treating this guy right here as a base. Well, the problem is when you look through the data booklet, I can't find any phenolate anywhere in any of these pKb tables. All right, so we don't have a pKb for that. All right, so how can we solve this? All right, so what we're going to do, we need to recognize something about phenolate. All right, and that is that it is nothing but the conjugate base of a compound called phenol. All right, so this is phenol right here. All right, and by the way, when I put this circle, that's just shorthand for these three bonds right there. So this is phenol, and think of this as an acid, and if it were to react with water and donate its hydrogen to water, all right, you get H3O+, and this would be what's left over from that, and that is phenolate. Notice that this is the exact same thing as that. All right, so that's why I'm calling this the conjugate base of phenol. All right, because when phenol is an acid, this would be its conjugate base. All right, so what does that let us do? Well, recall that there's this relationship between the pKa of an acid and the pKb of its conjugate base. All right, and that is that the sum of them has to add up to 14. So if we can find out what the pKa of this acid is, of phenol, we can figure out what the pKb of this guy is right there. And then we're in business to do this problem. All right, so going back to the data booklet, notice this first compound right here is phenol. All right, and it gives its pKa as 9.99. All right, so that's all we really need. because now that we know that the pKa of that is 9.99, we know that the pKb of this guy is 4.01. All right, and if we know it's pKb, we can calculate its Kb by just the standard transformation. All right, so we have this right here. All right, so this guy right here, again, it's a conjugate base, and if we have that stuff in solution, all right, it can, even though it's a conjugate base, it can act as a base. All right, it's going to act as a base with water, and if it does that, it would generate some of this. This is the now you'd say that this is the base and this is the conjugate acid. So this would be the expression, and we're going to do the same type of start, change, end expression. Hopefully you've seen that enough times that I don't have to go through that exactly. But for this particular reaction right here, this would be the expression. Remember, the stuff on the right is what goes up top. This guy goes down bottom. We fill in these expressions here. We can make that assumption that the denominator is essentially the same thing as this. We solve for x, and one thing that we can see is that x is the same thing as your hydroxide, and once we know that, we can go to POH, and from POH we can get to pH, which would be 12.19. All right, so 90% of this problem was the exact same as that previous problem. The only difference is that we had to use a little bit of logic to figure out the Kb. All right, and one thing to point out is this little process of figuring out the Kb from the Ka is something that we'll do a lot of when we get to acid-base neutralization problems. So it's not like this is a one-off time that you have to do this. Knowing this relationship between pKa and pKb is going to be a very useful tool. All right, so that's it for these problems, and I will give you some practice problems to practice doing this with weak bases.